So, good afternoon, everyone. So let's start off with the tutorial. So all this while we have been covering Z transform. So in the past few weeks, we have already covered Z transform. So this week again, we'll be focusing on Z transform. So let's start with this week's tutorial, right? So we'll start from where we left off last week. So that is from question number 3.32, right? So just going back to the textbook. Just going back to the textbook, question number 3.32 states that we need to show that the following systems are equivalent. So these two systems are given over here. We have to show that these two systems are equivalent, right? So since we are focusing on Z transform, so what we can do is first we can compute the Z transform of both the function and see what do we get at the end of the system, right? Or basically just to determine the transfer function of both the systems in order to see if both systems are equivalent or not. So if we do that, so for part A, if we perform the Z transform of the difference equation that is given over here, that is y of n is equal to 0.2, y of n minus 1 plus x of n minus 0.3, x n minus 1 plus 0.02 x of n minus 2. So if we directly perform the Z transform of this is what we get. And then we can further simplify it in such a way that we can rewrite it as h1 of z is equal to y of z on x of z. Then we'll be getting this particular term over here, that is 1 plus 0.3 z to the power of negative 1 plus 0.02 z to the power of negative 2 holding upon 1 minus 0.2 z to the power of negative 1. Now, what we can do is further simplify this by factorizing the numerator. So factorizing the numerator, will be getting this, right? And then what we can do is we can see the zeros and poles can cancel off, right? In this particular case, we can cancel that off and we will be left with 1 minus 0.1 z to the power of negative 1, which is equivalent to our h1 of z. Then computing the Z transform of the second difference equation that is given over here, that is y of n is equal to x of n minus 0.1 x of n minus 1. So again, performing the Z transform, this is what we will be getting over here. And then what we can do is we can write that in form of h2 of z, that is transfer function, which is equal to y of z upon x of z. That will give me 1 minus 0.1 z to the power of negative 1. Right, so you can see that the Z transform of both the equations, A and B, is giving me 1 minus 0.1 z to the power of negative 1. So in that particular case, we can conclude that h1 of z is equal to h2 of z, and both the systems are equivalent in that particular case. Moving on to the second question, that is 3.36, right? That is 3.36, yeah. So let's go to the question. 3.36 says to consider this system that is given over here, and we'll need to sketch the pole and zero pattern and determine whether the system is stable or not, and determine the impulse response of the system. So we are given a region of convergence that is 0.5 z is greater than 1, right? So this is the region of convergence that is given. So based on this, we can conclude that the system is a causal system, right? So anyways, so the first thing we'll need to do is to determine the pole and zeros and determine the impulse response of the system, right? So based on that, what we can do is we are already given h of z. So the first step is to try to factorize the numerator. So if we are able to factorize the numerator, because the denominator is already factorized, excuse me. So trying to factorize the numerator. So we'll be able to factorize the numerator. In this particular case, we'll be getting 1 minus z to the power of negative 1, holding into 1 minus z negative 1 plus z to the power of negative 2, right? Holding upon this particular term over here. And we can see that the poles and zeros can cancel off in this particular case. So once we perform that, we get this particular term over here. So what we can do, we just need to determine our poles and zeros, right? So our poles can be determined from the denominator, right? So basically we take this term and equate it to 0. you take this term and equate it to 0, while we can use the quadratic equation to solve for our zeros, right? So solving the zeros using the quadratic equation, we'll be getting 1 plus minus root 3j whole thing upon 2, while our poles will be half and 1/5. So based on this, we can see if our system is a causal system, if our main system was a causal system based on this particular region of convergence. So in that particular case, these two poles are inside the unit circle, and it will be covering the the region of convergence for this whole system. Will be actually including the unit circles. In that particular case, the system will be stable. So the next is to determine the impulse response of the system. So the transfer function is given over here. So we basically need to perform the inverse transform of this system in order to get our impulse response. So just before going to the impulse response, what we need to do, the first thing is to try to decompose this particular term over here using partial fraction, right? So performing partial fraction, will be getting 1 plus whole thing into 5/2 whole thing upon 1 minus half z to the power of -1 plus -2.8 whole thing upon 1 minus 1/5 z to the power of -1 whole thing is multiplied by z to the power of -1. So performing the inverse z transform and keeping in mind that the system is Gaussian, we get delta n, right? Direct z inverse z transform of 1 is going to give me delta n plus 5 times 1. I mean 5 into half to the power of n minus 14, 1/5 to the power of n whole thing multiplied by u of, it should be u of n minus 1 because of this delay that is introduced over here, right? So because that delay has been already factored into these two terms over here, so there should have been a delay over here that should be n minus 1, right? So yep. Anyways, moving on to the next question. Next question is y of n is, next question is 3.37. Compute the response of the system. So this is the response of the system. This is the difference equation given for the system. And we were given the input, that is x of n is equal to nu of n. And we need to determine whether the system is stable or not. So in order to determine the system response, that would be y of n based on this this particular difference equation that is given to us. So the first thing that we'll need to do for this particular term is to identify the transfer function, that is h of z for this particular term, or h of n for this particular term, right? So once we have determined our transfer function, that is y of z whole thing upon x of z, right? The transfer function in the z domain, right? So what we can do is also identify and transform this into our z domain. So once we have this term into our z domain and we have identified our y of z upon x of z based on this particular term over here, we can multiply the two in order to determine our y of z, right? So based on that, we can then perform our inverse Z transform in order to determine our system response, right? And then we can also use the system's output the system's output poles in order to determine whether the system is stable or not. Just by seeing this particular term over here, we can see this y of n is a causal, right? While x of n is also causal. Now, what we can do is to first transform y of n into the difference equation that is given. We will try to identify the transfer function, right? So first step is to perform z transform on this particular difference equation. So we'll be getting this particular term over here, right? So once we have this particular term, what we can do is we can identify the transfer function that would be y of z upon x of z, right? Which is equal to h of z, right? So we'll be getting z to the power of -1 plus z to the power of -2 whole thing upon 1 minus 0.7 z to the power of -1 minus 0.12 z to the power of -2. So this will be the this should be the transfer function that we attain from the difference equation that is given. right? Once we have our transfer function, what we can do is, again, we are given the input. So based on the input, we can transform the input into Z domain again, right? So transforming the input into Z domain, we'll be getting x of z is equal to z to the power of -1 holding upon 1 minus z to the power of -1. So the denominator is correct. So once we have our y of z and we have our y of z upon x of z, so what we can do is basically multiply x of z with y of z upon x of z in order to get y of z, right? So basically multiplying x of z with h of z will be getting our y of z. So doing that, we'll be getting this particular term over here, right? In this particular case. So now, again, the most simplest step is to first try to factorize or simplify the numerator and denominator. So in this particular system, we can factorize the numerator and denominator over here. So we'll be getting z to the power of -1 holding into z to the power of -1. I mean, z to the power of -2 holding into z to the power of -1 plus 1. Holding upon 1 minus 0.3 z to the power of -1, that is into 1 minus 0.4 z to the power of -1, that also is multiplied with 1 minus z to the power of -1 whole thing squared, right? So this is what we get. So now, in order to determine the impulse response, excuse me, in order to determine the impulse response, what we need to do is to first perform the partial decomposition of this using partial fractions. So we decompose this using partial fractions, right? So once we have done that, we'll be getting these terms and then using our Z transform table, to get our y of n, right? So we'll be getting over this as our y of n. Again, we need to determine whether the whole system was stable or not, right? Based on this, we can see that the y of n, right, based on y of n, we can just see that the region of convergence for this is based on this. The poles will be z is equal to 0.3, z is equal to 0.4, and z is equal to 1. So based on this, we can see that based on this particular term, if the system is causal, so this will be dominating or defining the region of convergence in this particular system. So in that particular case, our region of convergence will be actually not involving at all would not be involving the unit circle, right? So would not be including the unit circle. So the region of convergence would be basically z is equal to greater than 1. So in that particular case, the system will be unstable, right? 3.39 y of z, I mean 3.39. Just let me check the textbook. What was the solution given for 3.37? 3.37. Okay, 3.37. Oh yeah. Okay, anyway, so let's, I mean, it says the system is stable, but however, the system is not stable, right? Because of the region of convergence of this particular term over here, that is, that would give us that z is greater than 1, right? So that does not include the unit cycle in that particular case. So if the system is causal, it does not include the unit cycle, it is not stable, right? Anyways, so let's move on, right? 3.39. Sorry, let's see the question. 3.39, let x of n be causal sequence with z transform x of z, whose pole and zero plot is shown in figure 3.39. Sketch the pole zero plots and the region of convergence of the following sequence. So this is what is stated, right? So these are the two parts that we need to sketch the poles and zero plot for, and the region of convergence for these two terms over here. So in this particular case, we can see x of n is given as such, right? Based on these particular terms, we are already given the poles over here that is marked with x, right? While the zero is marked with an open circle. So this is my only zero. So based on this, we can derive our x of z, right? So deriving our x of z, right? So we can derive our x of z. So the only zero was at -1. So that would give me is the numerator term as 1 plus z to the power of -1, right? Because this will give me a 0 at -1, right? While using the pole values that I got from this diagram over here, that is my pole is at positive half and at minus half positive j half, right? And minus half negative half j, right? So based on that, this is what I get, that is 1 minus half z to the power of -1 into 1 minus p z to the power of -1 into 1 minus p conjugate z to the power of -1, where p is basically equal to -half plus half j, right? So the first question was to determine this is the term that is given there, that is x1 of n, which is equal to x of minus n plus 2. So what you can do is based on this operation, if you take out negative, and based on that, if you see that n, if you take out n, take out negative, so you'll be left with n minus 2, isn't it? So in that particular case, what you do is you first reflect and then you move 2 units to your right in that particular case. So if you perform that, you'll be getting that z to the power of -1 is the inverse, right? That is reflection, while this z to the power of -2 is two units delayed, right? The system is being delayed by 2 units. Or it basically, this graph is being shifted, right? You shift the graph to your left, to your right, isn't it? Towards the positive side of the axis. So based on this, our basically doing the z transform of x1 of n is equal to x of -n plus 2, right? Forming the z transform of that, we'll be getting x1 of z is equal to z to the power of -2, x of z to the power of -1. So we are already given x of z. So in x of z, we just need to substitute in place of z with z to the power of -1 and multiply the whole term with z to the power of -2. So we'll be getting this particular term over here, right? So based on this, you can see my 0 will fall at z is equal to -1, right? Z is equal to -1. And if I take this z, right, z to the power -2 could be read as 1 upon z to the power 2, right? So basically, what I mean is that we can take this from the numerator. We can write it at the denominator as z to the power of, power of 2, right? Like that. So if we do that, right, so we can take this as a pole, right, in that particular case. So based on that, the pole over here in this first term, that would give me a pole of 2, while the pole for these two terms would be 1 upon p and 1 upon p conjugate, while the pole for this particular term would be 0, right? This shouldn't have been there and there, right? Anyways, so we can basically plot this and we'll be getting this particular diagram for poles and zeros, right? The other thing is also to keep in mind, we were told to find the region of convergence. Again, the region of convergence based on this, you can see, right? You can see that in this particular case, this will give Z, the magnitude of Z should be greater than 2, while the magnitude of this should be greater than the magnitude. I mean, from these two particular terms, it says Z has a magnitude that is greater than magnitude of P. So the magnitude of P would be, that would be negative half and half. That should give me a magnitude of 0.707. So based on this, the first term will dominate, or will basically state that the region of convergence of the system is basically Z is sorry, excuse me. Sorry, based on this, the poles for this, the first term would be Z is less than 2, right? Z is less than 2, right? The magnitude of Z should be less than 2, right? Because the magnitude of total of these two, this term over here should be greater than 0 in order for the system to be defined, right? So the magnitude of Z in this from this particular term would be that magnitude of Z is less than 2, while these two terms would state that the magnitude of Z is less than 0 point, 0 point less than 0 0.7 0.070, right? So based on that, our region of convergence will flip, right? As earlier, our region of convergence for this particular term was Z is greater than half, Z is greater than 0.70, 0.07. So in this particular case, it will flip. Our region of convergence for this should be actually, just give me a second. Let me just see the question again. It is 3.9, right? Yeah. So in this particular case, our region of convergence for this term over here should be right. For this term, it is Z is less than 2. For this term, it is less, Z is less than the magnitude of P. And for this term, Z is less than the magnitude of P conjugate. So in this particular case, Z has the magnitude of P will be 0 0.70, right? 0.707, that is root of 2, right? So yep, that is sorry, that would be root of half, right? Sorry, excuse me. So based on this, that this states that Z's magnitude is less than half, right? Root of half. So in that particular case, the region of convergence should be so this should be the magnitude of Z is actually, right, let me just correct it over here, should be less than root of half, right? Or the other thing is, you can read it as the region of convergence is basically magnitude of Z is less than 0.707, right? So let me just clear and let's move on to the next part, right? Now, for the next part, that is part B of this question, that is basically we are given x2 of n is equal to e to the power of j by 1/3 to the power of n, I mean e to the power of j into pi upon 3 whole thing multiplied by n multiplied by x of n, right? So basically using these Z transform properties or just directly performing the Z transform, we'll be getting x2 of z is equal to x of e to the power of minus j pi upon 3 whole thing multiplied by z, right? So basically what this means is in place of z, which have to substitute e to the power of minus j pi upon 3 multiplied by z, right? So if we do that, we'll be getting this particular term over here. Again, if you see, this is just basically, I mean, first thing is to just determine our poles and zeros. So if we determine our poles and zeros for this, we'll see that the pole of this, the pole of this particular term over here gives me z is equal to minus e to the power of pi upon 3j, while the poles, excuse me, just taking the numerator over here, right? That will be for my zeros. So my zeros will be basically equal to z is equal to e to the power of j multiplied by pi upon 3. That will be a negative value of that, right? While the poles will be z is equal to half e to the power of pi upon 3j, right? While the other poles will be p times e to the power of pi upon 3j, while the other one will be p conjugate multiplied by e to the power of pi upon 3j, right? So based on these, the region of convergence does not change. It is just an introduction of a phase, right? In this particular case, so it is a phase rotation of pi by 3 counterclockwise, right? So phase rotation of pi by 3 counterclockwise. So whatever we got over here, in this particular case, we just rotated by pi by 3 anti-clockwise, right? So it just twist a little bit around 60 degrees, right? And the other thing is also the other thing is that the region of convergence does not change. It remains as of this, right? So based on this, the region of convergence was z is greater than half, z is greater than magnitude of p, z is greater than the magnitude of p conjugate. So in this particular case, that should have been z, the magnitude of z is basically greater than conjugate of p, right? Moving on to question number 3.4, right? Question number 3.4. It says we want to design a causal discrete time linear time invariant system with the property that if the input is x of n is equal to half to the power of n multiplied by u of n minus quota into half to the power of n minus 1 multiplied by u of n minus 1, then the output is y of n is equal to 1/3 to the power of n u of n, right? We need to determine the impulse response h of n and the system function h of z of the system that satisfies the foregoing system. Find the difference equation of the that characterizes this system. Determine a realization of the system that requires the minimum possible amount of memory, right? And determine if the system is stable, right? Just going back to the question, right? So the region of convergence for this term over here is just a correction. The region of convergence for x of z is basically z is greater than. So for this, we know that z is greater than half. For this, we know z is greater than the magnitude of p, that is z is greater than root of half, right? While the magnitude of this p remains the same when we are considering p conjugate. So based on this outweighs the region of convergence of these two, right? So basically the overall region of convergence is that z is greater than half, right, for this particular term over here. But in this particular case, we get the region of convergence that is z is greater than in this particular case, that will be z is less than 2, right? The region of convergence will be z is less than 2, while for this one, it would be z is less than the magnitude of p, right? While the magnitude for this particular term would be z is less than the magnitude of p conjugate, right? Excuse me, that would be the magnitude of, z is less than the magnitude of 1 upon p, right? So in that particular case, that would be 1 upon okay, so the region of convergence for this particular term would be z is less than 2, right? In that particular case, right? So that was correct. So pardon me, while the region of convergence for this does not change, right? It is as it is, right? Anyways, let's move on to the next part, right? So 3.4 again, let's go to the question again. So we were given these two terms over here. So we need to determine the impulse response and the transfer and the system function h of z of a system that satisfies the foregoing conditions. Find the difference equation, difference of equation that characterizes this system, and then determine a realization of the system that requires the minimum possible amount of memory, and D, determine if the system is stable or not, right? So the first step, we are given the input and output, so we need to determine the transfer function of the system, right? So based on this, if we are given the input and the output, so we can determine the transfer function, that is y of z upon x of z, right? So in order to do that, what we need to do is to perform the z transform of the input, right? Performing the z transform of the input, we'll be getting this particular term over here, right? And performing the z transform of the output, we'll be getting this, right? So in order to get h of z, we can just divide y of z with x of z, right? So performing that, we'll be ending up with this particular term, that is 1 minus half z to the power of -1, whole thing upon 1 minus 1/3 z to the power of -1 into 1 minus quarter z to the power of -1, right? Which is equal to, right? So again, what we can do is we can decompose this system using the partial fraction, right? If we do that, we'll be getting 3 upon 1 minus 1 upon 4 multiplied by z to the power of -1 minus 2 holding upon 1 minus 1/3 z to the power of -1, right? So in order to determine our h of n, basically what we can do is perform the inverse Z transform of these two terms. We'll be getting 3 into 1 quarter to the power of n minus 2 to the 2 into 1/3 to the power of n, whole thing multiplied by u of n. Since this system is causal, this is because our input is causal. You can see that our input is causal and our output is also causal. So that determines that our transfer function h of z and our system response is our system impulse response h of n is also causal, right? In that particular case. Part B, right? For part B, we need to determine the difference equation associated with this. So we have determined our h of z, isn't it? Right. So just keep it over here. Let's keep it over here. We have determined our h of z. So in this particular case, what we can do, our h of z is basically y of z upon x of z. So if we write this particular term over here, so that would be y of z upon x of z, that is equal to this over here, right? So then what we can do is take this term over here and multiply it with this, and take this particular term and multiply it with this, right? So once we do that, we can then find our difference equation, right? So multiplying that, by doing that, we get this term over here, right? That is y of z minus 7 upon 12 z to the power of -1 multiplied by y of z plus 1 upon 12 z to the power of -2 y of z, which is equal to x of z minus half z to the power of -1 x of z, right? So once we have that, right? So once we have that, now what we can do is perform the once we have this system, then what we can do is make y of z the subject of the formula. I mean, not the subject of the formula. We can leave this y of z and take the rest of these terms, right? We can take the rest of this term because this is because y of n will be our system output, isn't it? So we can take the rest of the system to the other side because these are delayed system. When we are drawing this, these are delayed output signal and that is fed back to the system, right? So we can take it to the other side. We can rewrite that, right? So if we rewrite it and perform the z transform of that, I mean the inverse z transform of that, the difference equation we'll get is y of n is equal to z 7 upon 12 y of n minus 1 minus 1 upon 12 y of n minus 2 plus x of n minus half x of n minus 1, right? So we have the difference equation on our hand now based on the transfer function that we obtained, right? Then what we need to do for part C, it says we need to determine a realization of the system that requires the minimum possible amount of memory, right? Reflecting back to chapter 2, I guess, right? Chapter 2, where we learned about direct form 1 and direct form 2. So based on that, our direct form, we learned that in order to reduce the amount of memories that is being used, we need to draw a system into direct form 2 form realization, right? So direct form 2 realization basically gives that efficiency or the system to have less amount of memory to be utilized, right? So in direct form 2, we use less amount of memory, right? So basically what we can do is draw the real, to realize the system with the minimum number of memory, we draw the direct form 2 realization of this particular difference equation, right? So this is what we get over here. If you have forgotten, please reflect back to chapter 2's note, right? Or chapter 2 of your textbook, right? Next is we need to determine whether the system is stable or not, right? So we need to determine whether the system is stable or not. So let's go to this particular term over here, right? Since if we draw the poles of these, right? If we draw the poles of these, we know the poles of these two, h of z or the system transfer function poles are at 1/3 and 1/4, right? So if we draw that, right, we have this. Sorry. Okay, let me redraw it. So if I draw it on an axis, right? So my pole is at 1/3 and 1/4. So 1/4, there will be one cycle at 1/4, and then there's another cycle at of radius 1/3. So in this particular case, what happens is the system is a causal system, right? So basically everything on the outside of the circle is being covered, isn't it? And the radius of this outer circle is 1/3, while the radius of the smaller circle is 1/4. So in this particular case, this 1/3, the outer radius is the region of convergence for this particular transfer function, right? So the region of convergence for this particular transfer function is the magnitude of z is greater than 1/3, right? Okay. So in that particular case, our region of convergence is greater than 1/3. So it includes the unit circle, isn't it? So if z is greater than 1/3, it includes the unit circle. So basically, z is equal to 1 is basically covered, right? So magnitude of z is equal to 1 is also covered, right? So if it covers the magnitude or the or if it covers that unit circle, right? So the system becomes stable. So the other way of realizing is if it's a causal system and if all the poles are inside the unit circle, the system is stable, right? So this is what is given over here, the poles of the system. P1 is equal to 1/3, P2 is equal to 1.4, are both inside the unit circle, thus the system is stable, right? So always remember, if a system is causal and all the poles are inside a unit circle, the system is stable. Moving on to question number 3.41, determine the stability region for the causal system, right? H of z is equal to 1/1 plus a1 z to the power of -1 plus a2 z to the power of -2, right? By computing its poles and restricting them to inside the unit circle, right? We need to determine the stability of the region, right? By computing its poles and restricting them to be inside the unit circle, right? So basically, we need to determine the stability region of this particular term over here. So based on this, right? Based on this, so based on this particular transfer function, you can see if by using the quadratic equation, we can determine the we can actually determine the poles of this particular system over here, right? So if, right, based on this quadratic equation, if a1 squared minus 4a2 is less than 0, there are two complex poles that are given by this particular term over here, right? Remember the quadratic equation, that is negative b plus minus root of b squared minus 4ac holding upon 4a, I mean 2ac, right? Isn't it? So based on that particular quadratic equation and substituting these two terms, we'll be getting the poles. But if a1 squared minus 4a2 is less than 0, this is the complex poles that we'll be attaining, right? Then restricting inside the unit circle, right? If we restrict these poles inside the unit circle, we'll get this particular term, right? So let's say let's say if we were to determine, I mean, if we square both the sides, right, and say that this system is less than 1, right, or inside the unit circle, if the poles are inside the unit circle. So what we can do is take the square of both the sides, right? If we do take the square of both the sides, we can eliminate this root sign, isn't it? So if we take the square of both the sides and restrict it to less than 1, so what happens, this term over here, it reduces down to a2 only, right? It reduces down to a2 is less than 1, right? So therefore, right, if we were to plot this on an axis of a2 versus a1, so based on this particular term over here, right? Oops, excuse me. Based on this particular term, a1 squared minus 4a2, we can get this particular curve over here, right? This is the curve that we'll be getting if we are plotting on a2 versus a1. So we get this particular curve, and then we also know if we restrict all our poles inside a unit circle, we'll get a2 is less than 1. So basically a2 is less than 1. So this shaded area is included. So this is what we get, right? Provided if the poles are complex, right? So if the poles are complex and inside the unit circle, this is the region that is being covered when we plot the variables a2 against a1, right? Now, if a1 squared minus 4a2 is greater than equal to 0, then there are two real poles, isn't it? So if we were directly to actually find the poles of this, we will be getting two poles. If a1 squared minus 4a2, so basically this is in the form of b squared minus 4ac, right? So if that a is greater than equal to 0, so we'll be getting two positive real poles, right? So in that particular case, we get two poles that could be represented by this, right? Then again, if we restrict it inside the unit circle, right? If we restrict both the poles inside the unit circle, so in that particular case, we'll be getting that the positive one, the P1 is equal to minus 8, right? The positive A1 plus this term over here holding upon 2, it will be our first term. That would be less than 1, while the other pole, that is minus A1 minus this particular term over here, right? Remember, this is a positive term. If that is, if we were to limit this inside a unit circle, that would be greater than -1, right? But less than 1, right? So this is what we get. So based on the condition, this is what we get. So based on these two terms, right? If we simplify this and simplify this, we'll get A1 minus A2 is less than 1, and A1 plus A2 is greater than 1, right? So based on that, if we have this, so if we draw this on this same axis over here, if we draw these two particular equations on this particular axis, so we'll get something like this, right? We'll get this something like this. So if we merge both the conditions, whatever we have found out, if we merge it, we'll get a straight line running through, right, this area, and then this area inside it is shaded, right? Right. So this shaded area, right, is the complex pole, right? The shaded red area is when the poles are complex, while these areas which is shaded in black are the regions where when we have real poles, right? So this small triangle that forms, that is within this boundary of 1, -1, and -1, right? And 1, this small triangle that is formed over here, it is said to be the triangle of stability, right? This is said to be the triangle of stability. Any pole that falls inside this particular triangle makes the system to be stable, right? So that's for question number 3.41, right? That's for question number 3.41. So moving on to the next question, that is question number 3.51. So based on the textbook 3.51, the question states to consider an LTI discrete time system whose pole and zero pattern is shown in figure 3.51, right? We need to determine the region of convergence of the system region of convergence of the system function h of z if the system is known to be stable. So if the system is stable, right? If the system is known to be stable, and this is the poles and zeros that are given to us. So based on this, we can derive our transfer function h of z, isn't it? So deriving the transfer function, we know that we have 3 poles and 1 0. So based on that, if we derive our transfer function, we'll be getting z minus 1 upon z plus half into z plus 3 into z minus 2, right? Where k is in any non-zero constant. So this k is just a scalar quantity to scale the transfer function, right? In this particular case, and these zeros and poles that we have got from, these terms, the zeros term and the numerator and denominator terms that we have over here is actually from the poles and zeros that we got from the diagram, right? So we're using the poles and zeros, we can write a transfer function h of z. So this is what we get. Since the system is stable, the region of convergence has to include the unit circle, right? So always remember, like I said, always when a system is stable, it has to include the unit circle right? So it's not just it is not just that the poles are inside the unit cycle, the system is stable. It has to include the unit cycle, right? So if we were to draw the if we were to draw the region of convergence of all this particular term, we can see for this particular term, the modulus of z is greater than half. The modulus of z is greater than 3. The modulus of z is actually greater than, it says the modulus of z is actually less, yeah, the modulus of z is actually greater than 2, right? So for this, the modulus of z is actually greater than negative half. The modulus of z is actually greater than negative 3, and modulus of z is actually greater than 2, right? Oh, sorry. Um, okay, for this particular term, the pole k is at minus half, right? For this particular term, our pole is at minus 3, and for this particular term, our pole is at 2, right? So if we were to draw the circle, it would be of radius 3. One would have been of radius 3. One would be of radius half. One would be of radius 2, right? It's over here in between. So in order to include the unit circle will be somewhere in between these two circles, right? The inner two circles, right? Over here, somewhere in between here, right? This place, right? So our region of convergence has to be within this region over here. Okay. So for that reason, our region of convergence, if the system is stable, our region of convergence is half is less than the magnitude of z, which is less than 2, right? That is the reason why this is the region of convergence that is chosen for this particular h of z, right? Moving on to part B of this question. Part B of this question states, it is possible for the given pole 0 plot to correspond to a causal and stable system? If so, what is the appropriate region of convergence, right? If it is possible for the given pole 0 plot excuse me. It is possible for the given pole 0 plot to correspond to a causal and a stable system. If so, what is the appropriate region of convergence? So basically, we have to determine the region of convergence in such a way such that the system is causal and stable. So in that particular case, if that is the case, if the system is causal, the region of convergence is this small circle encompassing all the poles. Thus, the region of convergence is absolute of z is greater than 3. So since the system is causal and the poles p1 is equal to negative 3, and p3 is equal to 2 lie outside of the unit cycle, we have a system that is not stable, right? So um, so based on this, what we can see is actually for the system to be causal, right? For the system to be causal and stable, it has to include the unit cycle as well as it should cover the region outside the cycle, right? That we are talking about. So in that particular case, we know this system could be causal if z is greater than 3, right? For this particular term over here, because we have, if the system was causal, the region of convergence for the first term would be z is the magnitude of z is actually greater than half. For this particular term would be z is greater than 3, right? Magnitude of z is greater than 3, while for this particular term would be magnitude of z is actually greater than 2. So in that particular case, this one dominates the region of convergence of z, right? So in that particular case, for this particular term, the region of for the system to be causal, this region of convergence for the system becomes the magnitude of z is greater than 3. However, in that particular case, the system is not able to cover the unit cycle, isn't it? So the region of convergence does not include the unit cycle, so thus the system will not be stable. So there does not exist a region of convergence which makes the system causal and stable at causal and stable both at the same time, right? How many possible systems can be associated with the pole zero pattern, right? And let's assume the system is we are not told the system is causal, so let's assume that. So we just need to determine how many systems can be associated with this pole and zero pattern, right? So in that particular case, there will be 4. One will be causal. If the system is causal, that is, if the magnitude of z is greater than 3, the system will be anti-causal if the magnitude of z is less than 3, right? That is another scenario. The other scenario would be the system would be non-causal again if the region of convergence falls between half is less than z. Z is greater than half and z is less than 2. And again, z is non-causal if the system could be non-causal for the region of convergence between 2 is less than z, which is less than 3, right? So there is a possibility of a total of 4 region of convergence in this particular case, right? Moving on to question number 3.53. So question number 3.53, a causal pole zero system is stable if its poles are inside the unit circle. Consider now a pole zero system that is stable and has its poles inside the unit circle. Is it always causal, right? Is it always causal? Right. Hint, consider the system h1 of n is equal to a n u of n and h2 of n is equal to a n u of n plus 3, where the magnitude of a is less than 1, right? So, yeah. So in that particular case, it says, so based on that, we get the answer is no, right? The answer is no. A causal pole zero system is stable if its poles are inside. Okay. It is not always true, right? It is not always true if a system's pole zero system is if a causal excuse me, a causal system is not necessarily stable if its poles are inside the unit cycle, right? It is not true. The system could be causal, right? For a given system h1 of a n u of n, its z transform is 1 upon 1 minus a z to the power factor 1, where the magnitude of a is less than 1. Right? This system is causal and stable. However, when h2 of n, right, this h2 of n that is given over here, a n u of n plus 3, in this particular case, the z transform is a to the power factor 3 z to the power of 3 whole thing upon 1 minus a z to the power factor 1. Again, the magnitude of a is less than 1. So in this particular case, the region of convergence does not include the unit circle, and right, the system is stable but is not causal in the particular case, right? So it is not necessary, right? It is not necessary if the poles are inside the unit circle. It is not necessary that the system is stable, right? As long as the region of convergence include the unit circle, the system is stable. So always remember the region of convergence has to include the unit circle in order for the system to be stable, right? Going back to this question, just again, please reiterating, I had made a mistake over here. So the region of convergence for x of z in this particular case, right? If you determine the poles of this system, right? And if the system is causal, right? So in that particular case, if the system was causal, so in that particular in the poles were as half, and p is equal to negative 1 upon, or I mean, p is equal to negative half plus half j, right? So in this particular case, this was given. So in that particular case, the region of convergence based on this particular term would have been z is greater than 2. For this would be z is greater than 1 upon p, while the magnitude of this would have been the magnitude of this would have been sorry. Okay, yeah. So this would have been, I mean, this term would have, if the system was causal, right, based on the poles we had have got based on this particular term, our region of convergence would have been z is greater than half. And for this particular term would have been z is greater than magnitude of p, right? Magnitude of z is greater than magnitude of p conjugate, right? For these particular terms of here that we have got. But based on this, the magnitude of p and magnitude of p conjugate are same, right? Isn't it? Because the magnitude is not affected, and this conjugate only affects its phase, right? So the magnitude of this p would have been, the magnitude of p would have been root of root of half, right? So the magnitude of p is root of half. So based on that, z is greater than half and z is greater than root of half. So based on that, this would have given and dominated the region of convergence for this particular term. So in that particular case, the region of convergence for this whole of this term would have been z is greater than half, right? So the region of convergence for this particular system is z is greater than half and the system is stable. Likewise, for this particular term, it would have been everything is inversed, right? So in that particular case, our region of convergence is also inversed. So it was greater than half. So in this particular case, our symbol, if it was greater than half, now it will be less than half, right? Everything is flipped. So we had the final value of half. So that is flipped and we get 2, while it was greater than half. So in this particular case, it is less than 2, right? While for this particular term, we are just changing the phase, isn't it? We are just rotating the phase. So the region of convergence does not change anyhow. The phase is affected, but the region of convergence is not affected. So it will remain as the region of convergence of x of z, right? So basically the region of convergence for this particular term would have been z is greater than half, right? So that is just a correction. Again, for the last question, going back to this particular question, the answer is no, just because just because if the poles of a particular system are lying inside a unit cycle, that does not make the system stable, right? The region of convergence has to include the unit cycle in order for the system to be stable, right? Okay, so always remember that. So that's it for this week's tutorial. See you next week, right?